back to another week of extreme value theory. This week we're going to look at extending our results about the extremes of IID processes to allow dependence between our observations. In this video we're going to consider how this sort of dependence is going to impact the distribution of block maxima. So in previous weeks we developed a lot of theory about the extreme values of processes where the underlying observations are independent and identically distributed. Last week, we looked at relaxing the identical margins part of this assumption, and this week we're going to look at relaxing the assumption on independence of the observations. And we're going to relax this to consider stationary processes. We have to maintain some sort of assumptions about the dependent structure that we have in our process, otherwise we can get any limit distribution at all for the distribution of rescaled partial maxima. We can see this by looking at a slightly contrived example. So if we have a stochastic process where the first term has an arbitrary distribution function f, and then we set every subsequent term in the process equal to the first term. In this case, our partial maxima are all just going to be equal to the value of the first random variable, which we saw has an arbitrary distribution function, in which case our partial maxima can also have an arbitrary distribution. So what we're going to do is restrict focus to stationary processes, and if we're doing that, we should probably have a quick refresher about what a stationary process is. If we've got a stochastic process, x1, x2, and so on, that's going to be a stationary process if the joint distribution of any t values in the process is invariant to translation by an arbitrary amount k. So in particular, if we're looking, for example, at the values x1, x2 up to xt, the joint distribution of those t random variables is going to be the same as the joint distribution of x1 plus k, x2 plus k, all the way up to x1 plus t plus k. In particular, what this stationarity assumption means is that the joint distribution of our observations is not a function of time. So if we have a stationary process, then what we can show is that a GEV type limit is still obtained if the sequence satisfies the asymptotically independent maxima condition. And that's what this expression is giving us. So this looks a bit horrendous at first, but what it's saying is that we're looking at two random variables, the maximum of two blocks of observations, the first of length I, the second of length j, and these are separated by qn observations. What we want is for any two block lengths, I and j, that the limit is the number of observations, the total number of observations, the distance between the blocks, and what it means to be a large value all increase. We want the dependence between those block maxima to go to zero sufficiently quickly. If we look at the term inside the absolute value here, what we see is that it looks a lot like a covariance term, apart from rather than using an expectation of the joint and marginal distributions, we've got the joint and marginal CDFs here. So what this means in plain English is that the dependence between block maxima diminishes quickly enough as things become large for a GEV limit to still hold. What should be noted here is that the GEV parameters for the stationary distribution aren't going to be the same as the GEV parameters that we'd get if the process were IID. We can link the two of these together by introducing an additional parameter, which we're going to call the extremal index theta, and that's going to take values between 0 and 1. The extremal index comes in as a pre-multiplier in the exponent term of the GEV distribution function. And we can use this to do a little bit of algebraic manipulation and work out how the extremal index is going to impact our parameter values for the GEV. But what we're going to spend the rest of this lecture looking at is what actually is this extremal index parameter theta. How is it defined? So in general terms, theta is a measure of the short-term extremal dependence within our stochastic process x. In order to define what theta is formally, I'm going to introduce a little bit of extra notation here. So we're going to take our original process x and use the probability integral transform to transform it onto standard fresh air margins. And we're going to call that transformed process y. We're then going to introduce this random variable m subscript to Pn, which is going to be the largest value of y2, y3, up to yPn. And we're going to let the largest subscript here, Pn, grow as n becomes large, so considering the maximum of a larger number of random variables. And we're going to let this index grow in such a way that Pn becomes insignificant to n as n becomes large. And there's a more formal definition of what this little o notation means at the end of the notes if you're interested. So using this additional notation that we've just introduced, we can define the extremal index theta to be the limit as n goes to infinity of the probability that the largest of y2 to yPn is less than n, given that y1 is greater than n. This is the limiting probability that the largest of the next Pn observations is not big, given that our current observation is big. So let's take a minute or two to think about this and come up with some properties of theta. Since it's a probability, we know it's going to be between 0 and 1. And note here that the brackets have changed relative to the previous result. We can have a theta value exactly equal to 0, but our previous result about the change in the GeV parameters isn't going to hold in that case. When when events are independent, this is going to give us a theta value of 1, but the converse relation doesn't hold. You can construct dependent sequences that have an extremal index equal to 1. If our process becomes independent at large lags, so if your process is no longer dependent at a lag greater than m, then our extremal index value is going to take a value greater than 1 over m. And another property of the extremal index is that it tells us how many large values we expect to co-occur. So the expected number of extreme values per cluster is going to be given by the reciprocal of the extremal index. And as I mentioned before, special care has to be taken in the case where theta is equal to 0, because not all of the properties are going to be well defined in that case. So in this video, we found that the GeV still holds for block maxima as long as the dependence decays within that process sufficiently quickly, and we defined what it means for that dependence to decay at a sufficient rate. Next time, we'll look at how this sort of dependent structure is going to impact our results for the point process and the peaks over threshold approaches. Thank you for your time, and I look forward to seeing you in the next video.